Hello students, welcome to another session of JEE advanced classes, chemistry classes. So today's topic we will be seeing carbonyl compounds, and which is a very important topic in organic chemistry, and you will see so many named reactions coming in this chapter, and even we have not all aldehydes and ketones, even we consider acid and acid derivatives also under this topic. So there are so many named reactions that are coming because carbonyl compounds, we basically treat it as two classes, where the carbonyl compounds basically means the compounds which contain C double bond O. So it exists in aldehydes, ketones, acid and acid derivatives also. So when we consider the aldehydes and ketones, they undergo like this C double bond O containing compounds, mainly they are behaving like electrophiles here. So they react with nucleophiles. So among this, let us say suppose aldehyde and ketone if you take, they react with nucleophile and undergo nucleophilic addition reactions. Whereas these acid and acid derivatives like carboxylic acid, acid halide, esters, acid anhydride, amides, they undergo the nucleophilic substitution. So that we treat them as two classes. So they have a part of that are undergoing nucleophilic addition and another one undergoing nucleophilic substitution. So the so many named reactions are coming. So we'll just revise again these topics and these let us say some questions in it take up and we'll discuss this. So let us see first one. The correct statement regarding the following scheme. So there is a ketone. It was treated with an amine. It is a secondary amine. Then it is giving a mixture of compounds. Then later it is treated with the ETBr, ethyl bromide. Then it is acidified or hydrolyzed. Then it is giving a mixture of two other compounds. So there are compounds mentioned U, V, W, X, Y, and Z. So what is the reaction actually? So when a ketone or an aldehydes, when treated with let us say ammonia derivatives, NH2. So let us see, suppose a basic equation of these is a C double bond O containing compounds. When they are treated with ammonia derivatives, like suppose you have H2N, then it is reacting with G, then it is giving C double bond N G. So if it is G is you are replacing with some other things, groups or a group of atoms, then you will get different compounds. Suppose it is NH3, so H2NH, so this will be NH, then it is amine. If it is hydroxylamine, H2NOH, then it is C double bond NOH, call them as oximes. So you are saying hydrazine, H2N, NH2, then we say C double bond NH2, then we call it as hydrazone, 2,4-DNP, 2,4-dinitrophenyl hydrazone. So these are the basic reactions that we generally consider under that class. So these are actually nothing but you see like R. So what we treat this as like a primary amine. So primary amine which contains H2, then it is undergoing what we call this characteristic reaction here as nucleophilic addition and elimination process. So this is addition elimination reaction. So first it is added, then it is getting eliminated. So in this case, suppose it is a secondary amine, then what is the product you are getting? So if it is a secondary amine, then also the same way you see the nitrogen attacks at the carbonyl carbon, pi bond shifts OH, then this OH group and this hydrogen at the adjacent position, they can be lost. So what you see is when it is suppose a secondary amine, that is you write it as suppose like this, N, R and R. So first it was forming C, OH, N, R and R. So there is a carbon at least, let us say CH3. Suppose this is R. So this is CH3 and this is R. So that R may be hydrogen, then it is aldehyde. If it is a ketone, then R is an alkyl group, then it is a ketone. So this is now what is the first addition product what you get. Then there will be elimination. That is in the process what we are doing is we are just acidifying the solution because it is acid catalyzed process. We can't use a higher concentration. So the pH has to be at an optimum pH in an acidic condition like 4.5 to 5.5. So there the addition elimination reactions are taking place here. So what is this is now? This OH group in presence of acid when you are heating it, this OH group is lost and the adjacent carbon hydrogens will be lost. So you will see CH2, N, R, C, double bond, N, R and R. So what do you call these compounds as? Enamines. So the alpha carbon must contain a hydrogen. Then it happens. So here the alpha carbon is having the hydrogens. So you can get the enamine there. So what is that enamine that may form? This is an alpha, this is an alpha. So double bond can form at this side, double bond can form this side. So what is that mixture is? It's nothing but a mixture of U and V. Okay. Then later if it is treated with ETBR, where the nitrogen lone pair in this case with this pi bonds in this case or in this, it is in conjugation. So this pi bond will form again, this pi bond will shift here as a negative charge. So similarly happens here in this case also. So this carbon may behave like nucleophile now. This carbon may behave like nucleophiles again. So these carbons are again still behaving like nucleophiles again. So this is what we call it as Stark enamine reaction, where the alpha carbons you are actually doing conversion into some alkyl groups. You are substituting in that position. Then you hydrolyze it so that you will get for the original molecule, you will get alkyl substituted things. So the Stark enamine process. So the Stark enamine process is we form a aldehyde or a ketones, mostly ketones. We convert into first enamines by reaction with the secondary amines. Then they are alkylated in the alpha position by reacting with alkyl halides. So this was the characteristic reaction that we see. So what it should happen is this carbon will be obtained with ethyl group, means you will get X from V and we get W from Q. So then it is hydrolyzed and acidified condition. So you will see the again the secondary amine was coming, but it gets protonated here. So that's why it may exist like this. So now what is the process? What we say, this mixture of compounds is nothing but U and V. This mixture is nothing but U is resulting W, whereas V is resulting X, and it may have a mixture of even the Y also may exist in this. So W, X and Y will exist in this mixture. So what is this mixture 2? This is W, X and Y. So now let us see the options. U and V, first one is U and V is a mixture in 1 and percentage of U is more than V. So is it correct? U is more than V, since this hydrogen can be lost easily compared to this hydrogen. Clear? So U is more than V. So because there are 2 hydrogen, this is alkyl methyl group. So this hydrogen can be lost easily. Less bulky, base is there. So the less hindered side, this will form this. So percentage of U is more than V. So this is correct. Next, The major component by moles in the mixer 2 is Y. So anyhow, this is only 1 mole. Suppose you take, you will get a mixer of this, means mixer of U and V. So this mixer may be 1 mole of the ketone is converting a part of this into this, a part of this into this. So the mixer 2 which contain W, X and Y, which is containing, let us say, some moles of means let us say this is, suppose you are getting higher percentage as we said in the first statement. Let us say this is suppose 0.7 moles. This will become 0.3 moles. So that what is this is? This is obtained from U. So this is, you will get 0.7 moles. This we get 0.3 moles only. Okay. But what is this thing now? Why? If you see, this is 1 mole is reacting and this 1 mole is reacting. So that we should get finally 1 mole of this only. So 1 mole of this will you see finally. So the number of moles of Y, clear. Major component of mixer 2 is Y, okay, correct. Then percentage of X is greater than W. Percentage of X is greater than W, so not correct. W is greater than X, so this is wrong. So a part of this statement was correct actually. So where Y is the number of moles higher in percentage, but the percentage or what is the component that is X is greater than W, which is a wrong statement. Now let us see this thing. W is formed from V. No, W is formed from U. So this is anyhow wrong. Now first statement itself says. Then U gives a mixture of W and X. So it cannot resonate like both ways. This carbon only can get nucleophilic character because of the resonance. So you can't get two sides here. So U will not result in W, X and Y. Similarly, what he is saying is V also is giving a mixture of W, X and Y. No, we will get W from only U, because the conjugation system says this carbon become nucleophilic or this carbon become nucleophilic because of this. So it cannot be 2. So this is also a wrong statement. So only the first statement is correct for us. Okay. So this is, let us say, the star kinamine or maybe hydrogen or ammonia derivative reaction first. So let us see the next thing. So I think this is. So the following reaction is carried out. So it is mostly like, if you see immediately what you see in the reactions is we are doing the alpha carbon halogenation. So this carbon halogenation we have done. Then we are saying, suppose we are getting these products with 1 mole of this compound, 1 mole of this compound. What is this process is? Nothing but we say haloform reaction. So during the haloform reaction, alpha carbon hydrogens are replaced with halogens. Then it proceeds in that way, finally giving the haloform. So the alpha carbon is this. So this is alpha carbon for us. So it has to be halogenated during the reaction of alpha hydrogen containing aldehydes and ketones when it is treated with alkalis in, let us say, bromine or halogens like chlorine, bromine or iodine is used, that alpha carbon hydrogens are replaced with halogens. So here what we are seeing is this carbon hydrogens will be replaced. But what you see immediately in the process is, let us see in the next page we will discuss and then we will come back to this and attempt this. So here when we just consider first, same thing we say, suppose pH right, instead of benzene ring, C double bond, we have CH2 and CH3. So we have taken 1 mole of this compound. So first we are reacting with, suppose with a base like OH minus, we will abstract the hydrogen from this carbon. So OH is abstracting this carbon hydrogen. So it is giving pH C double bond O, CH minus and CH3. But this carbon, like you can say, this is resonance stabilized. So the enolate ion will form. So this carbon negative charge converts like this and forms an enolate. So pH CO minus, double bond CH3. But these are behaving like nucleophiles. We have an electrophile within the process. The bromine is there. So bromine reacts with this. So at this stage now bromine is acting as a new electrophile, the Br leaves. So directly way of writing this. So let us say pH C double bond O CH Br CH3. Now this behaves like more acidic than this. So first, if you assume in the 1 mole, you say 1 mole of this compound or 1 molecule of this compound is suppose reacted. So 1 molecule of this will convert into 1 molecule of this. So now what we have is 1 molecule less in it, 1 molecule, and you have maybe let us say 100 and let us say 1. 100 molecules are there. 99 molecules exist and 1 molecule of this will form. But this is more acidic than this compound. So the next base will abstract the hydrogen from this. So base is abstracting suppose again hydrogen from this. What do you see? Generally haloform reaction we just normally continue it. But the major thing in this here, this hydrogen are more acidic than that hydrogens. Because bromine is there, if carbon gets negative, it may be delocalized onto the oxygen. It may be delocalized into empty orbitals of halogens. So whether it is a chlorine, bromine or iodine, their carbon negative charge can delocalize into halogen empty orbitals also. What we see is this hydrogens becomes more acidic. So after monohalogenation, the hydrogens if they are there at alpha carbon, they behave like more acidic. So the base has to abstract this hydrogen again because it is an acid base reaction, which is more faster than that. So now you will see pH C double bond O C minus Br and CH3. Now this again will be brominated at that. So pH C double bond O C Br and CH3. So this one molecule immediately converts into this. So this one molecule immediately converts into this. So during this process what we had is, when you see one molecule of this is reacting immediately giving this, then one molecule of this is immediately converted into this. So after that the reaction has to be only electrophile reaction, nucleophile reaction when the base reacts at this. That is the last step in the haloform, when alpha hydrogens are replaced. It is not haloform completely because it is not CH3. So all alpha hydrogen when it is replaced, then the OH minus starts behaving as only nucleophile. But in this case, now what is happening? One molecule of your ketone finally converted into dihalo compound. So remaining let us say 99 molecules are there. They are again acidic. Base is there. So the base again can react at that. So what you are doing is, you are continuing this acidic hydrogens into later stages. Means converting into monohalogenated then into di. So how many molecules of bromine reacted in the total process? 1 mole reacted here, or 1 molecule reacted here, and 1 molecule reacted here. So what we have started is, we started with 1 mole of this and 1 mole of bromine. But every 1 molecule of ketone is reacting with 2 molecules of halogen to give this product. 1 molecule of this. So if you just reciprocate it and see that, what happens is, if 1 molecule is converted to 1 molecule with 2 molecules of this, if you assume this one, half molecule reacts, half moles reacts. So if 0.5 moles of this reacts, you will see the consumption of bromine 2 times. Means 1 mole of bromine has to react. And to give 0.5 moles of this. Clear? So what we see during this halogenation process, because after monohalogenation, since the hydrogens becomes more acidic in this case, they get immediately replaced. So instead of your ketone is reacting. So what we see, half molecule, half mole of this will be left, 1 mole of this gets consumed, you will get 0.5 moles of this is formed. So every 1 molecule was consuming 2 molecules of bromine or halogens here. So you will see the dihalogenation immediately. Then the base will starts reaching this. So next molecule converts, next molecule converts. So similarly, if you go on doing it like that, then you say half mole is suppose consumed, your 1 mole of bromine has to consume. So the half mole has to left in it. So now, if you go back and you will see the answers, you can identify the answers. So now what is happening? 1 mole of S is formed. This one, no, this immediately gets converted to this. So the reaction will not give only S. So this is wrong. 0.5 moles of T is formed, X. So 1 mole has to react with 0.5 moles here. So 1 mole of bromine is consumed, so 0.5 moles of this you will get. So 0.5 moles of R is left unreacted. So R is this, same thing. So half mole of this is left, so which is also true. Now 0.5 moles of S and 0.25 moles of T are formed. No, because as it is formed, this immediately starts converting into this. So this won't exist. So if half mole is this is forming, suppose, then it may be converting into this. So that is why you may be saying the next 1 molecule is reacting in this. So not like that. This is also wrong. Means you have to wait first 0.5 moles, 1 mole of this first finally. Okay? Because the reaction is after first halogenation, then immediately the base starts reacting at the monohalogenated, not at the first. If it reacts at the first, then this might be the option. So then your first option and last option also may become correct. But it won't happen like that. Okay? Then. So let us see the next. So Rainy, like if you just see question, Rainy is preparing the following compounds by aldol condensation using dilute NaOH as a base. How many of them was she successful? So it's a name of a person who is preparing, trying to synthesize these compounds. Now among this, how many she could able to do it possible? So what happens in the aldol condensation is alpha carbon hydrogen containing compounds when treated in presence of alkali and heated. So you can do in presence of acid, you can do in presence of base. Then the heating also can be done in presence of acid, can be done in presence of base. But you just say the conditions are there. What are the conditions is? If it is acid catalyzed, it proceeds by inhalation, inhalation and proceeds. It is in the base process, it proceeds by carbon anion formation and proceeds. And dehydration which happens, or the condensation which happens in presence of acid proceeds by E1 path. In presence of base, it proceeds by E1CP path. So all this, like let us say background of that aldol condensation. But now, in this case, what is we are seeing is, maybe there is a suppose a compound which is aldehyde and a ketones existing in the same compounds, or you are reacting an aldehyde and a ketones, or ketone and ketone of different ketones. When you are reacting it, 2 or different aldehydes you are reacting, then in such case, which type of compounds you may generally see formation? So generally we say aldehydes are more reactive than ketones. So when there is a carbon anion is formed at a carbon anion is formed through aldehyde, or carbon anion is formed through ketone, it has to react mainly at aldehyde, not at ketone. So what we see is, when we try to synthesize a compound where ketone is more reactive than aldehyde, that may not be the case. That may not be your possibility. So let us see in the process what you see. When we just see aldol condensation, what is the final product for us? It's an alpha beta unsaturated aldehyde or a ketone. So now, how many of them she is successful in synthesizing it? So just to see this compound, suppose you said this is CH2 now, simply. So what we have to do is, you have to break this one. You can write O and CH2. So this compound, what we are getting, CH2 double bond, this is CH2 double bond CH. So what can be this compound is? This you just break it, you write O, and this side you can write CH, means hydrogen. So O and H2. One case, clear? Or we can write H2 here and O here. Means it has to become CH3. Let us say now this may become now as per this what we say. So you write this is O, this is H2. Then this side you can write H2, otherwise. Then this side O. Means you may create this as aldehyde. This will become CH4. Will it be reactive? No. So can I write H2 and O is this way? So this option is not correct in this case. Maybe other cases it may be true. So what is aldol condensation product? You try to break one side, C double bond C, unsaturated carbons, double bond carbon, double bonded carbon. You can write O here and H2 may be here, or O here and H2 may be here. So reverse, if you try simply. So this is not a possible case. Anyhow, this has to be an aldehyde and alpha cut. So two molecules should be like that. Clear? So now let us see the condition in this. So this is now formaldehyde, and this may be now CH3, C double bond O CH3. So what we did is carbon anion was formed here, and this is reacting at aldehyde carbon. So it can be, but this is not alpha hydrogen containing, this is alpha hydrogen containing. But this will favor Cannizzaro, this will favor aldol. But what happens is, aldol takes place, but not Cannizzaro. Because aldol reaction first step is acid base. Cannizzaro first step is electrophile nucleophile. So as long as there is a possibility of aldol condensations or aldol reactions, then Cannizzaro reaction will not take place. So now what will I see? So this is now forming a carbon anion having only alpha hydrogen in this. So this can lose 2 hydrogens, this can lose O. So this is okay. This can be prepaid because formaldehyde is more reactive than ketone. Okay. And next, in this if you see, try to break like this. So you can write O here, H2 here. Means you make this carbon as CH3. So let us say next, it can write O here and H2 here, which is a possibility. So there are only one thing you are seeing always. The other side, if you write O, then only it is possible to give 2 ketones, 2 aldehydes, a ketone and aldehyde. But one side you are writing, it is converting into, let us say, like a hydrocarbon type. Then it is not at all possible. So what do you see? This you can't write now. Means what is this condition is? You can say this hydrogen addition here, this oxygen here is wrong. So you have to write O here and H2 here. So what is this compound now? This carbon doesn't have any hydrogen. So what is this now? Is CH3CHO, CH3CHO plus this side it is nothing but CH3CH2. So CH3CH2, C double bond OH. So we are getting both aldehydes. But now what we did? This alpha carbon less reactive. So otherwise if you now see, What is this question basically is less reactive should form a carbanion ion, more reactive aldehyde or a carbonyl group should react. So, more reactive carbonyl should lose oxygen, less reactive carbonyl compound or aldehyde or a ketone should lose hydrogens in alpha position. So, this is less reactive, this is more reactive, this is losing O, this is losing H2, because we are writing H2 here and O here. So, this is also possible. Yes. Now, next if we do in this, so let us do in this now, what I can do? We can write O here and H2 here again. So, this is formaldehyde and again, this is nothing but now ketone, some other ketone. So, HCHO plus, we write like this simply, CH2, then C double bond O, CH2. So, this is C double bonded O. So, these two compounds, so this alpha carbon hydrogens or this alpha carbon hydrogen can be lost, but this carbon is better nucleophile than this because there is a bulkiness in this side. So, this is losing, this is also possible, okay, because formaldehyde is losing oxygen, this less reactive carbonyl is losing hydrogens. The next, so how many? So, here it is an like integer type because you have some numbers. Next in this, to break this side, then this is O, this is H2. Okay? So, this side you can't write H2 because if you write this H2 it becomes a hydrocarbon. So, this is nothing but now H2, this is O. So, what is this now? The ketone, acetone, CH3, C double bond O, CH3, this part. What is this is now? CH3, C double bond OH. So, what we are seeing is hydrogens are lost in aldehyde, oxygen is lost in ketone, which is not true because hydrogen mainly should be lost in ketone, less reactive, and oxygen is lost in presence in more reactive. So, aldehyde should lose oxygen, this has to lose hydrogens. So, this is wrong, it cannot be possible because when carbon ion is formed in aldehyde, it immediately reacts with aldehyde. When ketone is forming carbon ion, it immediately reacts with aldehyde, but not with ketone. So, when we see the carbon ion is formed in this, it may react with this, it won't react with oxygen. That. So, if carbon ion is formed in this, it may react with this, not with that one. If possible, you write all, but when you try to synthesize, you are getting in very minute quantities because less reactive carbonyl should not be more favored for nucleophilic addition. So, this is not possible. Now, in this, break this side. So, this is O, this is CHO. So, this is a ketone, this is an aldehyde. So, aldehyde is part is reacting, means losing oxygen. So, maybe you have written like this. No? So, sorry, this is CH2. So, this is CH3. Sorry, I should write. So, this is CH3. This is CH3. Because H2 we added here. So, this is O, this is a ketone, this is a ketone. Anyhow, only keto groups are there. So, this CH2 hydrogens can be lost. No, because this carbon, you can write two possibilities in this. Okay. Two possibilities are there here. So, we write O here or H2 here. Now, what is the other possibility we write? So, when you write H2, there is no alpha hydrogen in this. So, you can't say this is H2. So, this combination is wrong. So, what is the other combination? This is H2, this is O. So, what is your compound maybe is? You have a C double bond O, this is CH. Okay. Let us write clearly little. So, this is double bond O. Clear? So, this is CH3, this is CH3, this is nothing but CHO. So, this alpha carbon hydrogens are reacting at more reactive. So, this is also correct. So, E is also correct. So A was correct, B was correct, C is correct, D is not wrong, D is correct, incorrect. Next, you can break in this. So this has to be now O, this has to be H2. So alpha carbon hydrogens here. So there is other combination will not work in this. So this is oxygen, so this is aldehyde, this is aldehyde, this is alpha carbon. So you may react this one with this, you may react this one with this. This is also true. Just try to see carefully. So this is hydrogen, alpha carbon hydrogen reacting with aldehyde because this has hydrogen here, CHO. So this carbon may react here, you will result it same 1, 2, 3, 4, 5, 6 member ring you will see. Then this CHO will be left like that. Next in this, break this. So this is hydrogen, this is O. But this is aldehyde, this is a ketone. So you can't get like this. More reactive should give oxygen and hydrogen should be lost from the less reactive. This cannot be possible. Next to this one. So this is H2, this is O. So this is a ketone, this is a ketone, but both are ketones. Problem. You can get it. Next, this one. This is O, this is H2, this is a keto side, this is a keto side. It is both are keto, no problem. But more reactive or less reactive, you can see also. Same. CH3 is there here, CH3 is there here. There is same thing is there. Here also the same. C double bond O CH3 is there, C double bond O CH3 is there. So that also is okay. Even they are diketo. In this case, break this side. This is H2, alpha carbon to this C double bond O. This is O. So this is aldehyde because this has hydrogens. This carbon has hydrogen. So this is aldehyde end. This is a keto end. This is also possible. Now this one, break this side. This is O. This is H2. So now what is it? This oxygen is an aldehyde oxygen. This is ketone hydrogens. Okay. Next, this one. This is H2. This is O. So this is aldehyde again. This is ketone also. So how many are correct? Means how many we had? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 totally. Which are incorrect, which are not possible in this? The D, G, that's it. So 10 are possible. 10 chicken synthesize. Okay. Next, coming to now this one. Consider the following sequence, that is a synthesis of cis, that is a jasomone T, this compound. Jasmone. By a scientist like McMurray, he is prepared, they are preparing that. Now during this, it is treated with, first this compound is treated with excess of sodamide, then ATI, next hydrolyzed or acidified simply, then reaction with SOCl2, then reaction with NaNO2 DMSO, then forming this product, that is Q. That Q we used here. It is treated with an alpha beta unsaturated, then it is IPRNH, it's a base amine, then TiCl3 reaction, that is conversion of generally NO2 group into what you see is C double bond O. So this is nothing but the hydrolysis by that. Then heating that NaOH and heat it. So it looks like mostly the compound is maybe converting into now. So this may be an aldol reaction again maybe. Then this is hydrogen, palladium, barium sulfate. It is conversion of, we are seeing the triple bond there. So it's a conversion of an alkyne into an alkene maybe. Okay. So as you just see the reactions here in the sequence. So let us see. So there is a triple bond. So this reaction indicates like a conversion of a triple bond into double bond. So now what may be the reactions? So NaNH2 when reacting with this. So let us write the compounds here and let us see what are these P, Q, R, S, T. Okay. So let us see this one. There was a triple bond first, C, triple bond C, then there is a chain like this. So let us see how many carbons are there first. We just this C and C, then C, 1, 2, 3, 4, 5. So after that we have OH. 1, 2, 3, 4, 5, then we have OH. When this is suppose treated with excess of NaNH2. So what will be the reactions here? This is a stronger base. NaNH2 is a stronger base. It immediately abstracts the hydrogens. So it abstracts the first acidic hydrogen. Which is more acidic here? Suppose anybody is asking it. This is a terminal alkyne. This hydrogen is acidic. This hydrogen is acidic. But alcohol oxygen is more acidic than the terminal alkyne. So the NaNH2 first equivalent will remove the oxygen hydrogen first. Means OH, alcohol hydrogen. Then it removes the terminal alkyne. So that you will see when it is treated with excess, it converted into C minus, triple bond C, Na plus will exist, Na twice. Then C, 1, 2, 3, O minus and Na plus. Okay. So both they are becoming a nucleophilic center, but this carbon with negative charge is a better nucleophile than oxygen with a negative charge. So what it will do? If it is treated with ET, so what we treated is ET, I think, some alkyl iodide. Huh? So that alkyl iodide will be undergoing nucleophilic substitution. So there is one equivalent might be used. So this will be immediately replaced with this carbon will be reacting with this ET. So this will give C2H5 C triple bond C O minus So I think if you just see what is, this was the original compound what we treated, then it is treated with one equivalent of this is excess, we get P. Then it is treated acidified SOCl2, NaNO2 DMSO. So let us go that was the P for us, which is what we got. So now this is our P. Now this is treated with first H3O plus, means just only protonated. So this O minus will become OH. So it is C2H5, C triple bond C, then OH. Okay. Now this is treated with SOCl2. Because it was not Q. Q was after NaNO2 reaction. So the OH will be replaced with Cl, the thionyl chloride, which is a better process to convert OH or replacing the OH with Cl. So it is nothing but C2H5, C triple bond C, then Cl. Okay. Now this is treated with NaNO2 in DMSO. So now what it should give? C2H5, C triple bond C, this Cl will be replaced with NO2. So you'll see his reaction is like SN2 type NO2. Okay. Nitro compound here. So this is our Q. So the questions were on what you see, what are there that we will see. But let us see final products. So this Q was treated with this one was there, I think. It's treated with CH2 double bond C, this one, with in presence of base. So what it may give at this stage, let us see. So what it will give if it is reacting with CH2, C double bond O this. Clear? So it's a conjugated compound. In presence of base you are doing IPR2NH. So this NO2 is an electron with drying group. This alpha carbon hydrogens will behave like a better acidic, or it can be tetramerizable. So these alpha carbon hydrogens are abstracted by this base. Then this carbon will behave like a nucleophile, but this is undergoing addition reaction. Conjugated carbonyl compounds, when treated with a nucleophile, mainly undergo 1,2 addition or 1,4 addition. But this carbon is a better, let us say now, negatively charged. So it can't approach at this carbon, it approaches this carbon, which is less sterically hindered. So this bulky carbon with NO2 groups and this completely, it can't approach this carbonyl carbon, it approaches this. So what you see the product of this two in presence of base, which is our R actually. C2H5, C triple bond C, this is NO2, this carbon is reacted at this. So this is CH2, then CH2, then C double bond O. So this is CH2, this is CH1 becomes CH2. So 1,2 addition reaction take. Or 1,4 you say actually, but it will tautomerize later into this. So this is our R. Okay, because this pi bond will shift as a double bond here, this one negative. So you will see OH and double bond here. But here it is enolic form, it is converting into keto form. So now next, this is R. Now what is it is done? It is treated with TiCl3. So this NO2 group, so with the Cl3 titanium trichloride in water, aqueous condition, this NO2 attached carbon should convert into C double bonded O. Means it converts into keto group. So it is C2H5, C triple bond C. So this is double bonded O. Clear? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. So this is C11. What is given there? This is S, I think. R in the sequence. So C9H something that what we had. So you can write that. Now you can see this. So C11 H16 O2. So C11 H16 O2. So this is our, let us say, S was. This is S now. So just see carefully. First it is treated with sodamide, then it is treated with ethyl iodide, then acidified, then SOCl2, then SOCl2 reaction with NaNO2 DMSO giving this. Then this is treated with the conjugated ketones giving this R. Then this is TiCl3 conversion into C double bonded. Now this one. So if you just see product, this C11 H16O2, this was treated with sodium hydroxide. So that is an aldol reaction again for us, because this compound has alpha hydrogen containing. Okay. So this keto group, already we said which one will be more reactive, which one will be less reactive. This keto group is more reactive than this, because this side it is bulky groups are attached, but around this you have a CH3. This is only one group, means total complete group is that. So this C double bond O is more reactive than this C double bond O. So alpha carbon of this should react with this carbonyl during the aldol reaction there. So what is that now? Let us see. So let us write in the next page. Have that page. So here itself we write. So reaction of NaOH and heating. What it will do? This alpha carbon or this alpha carbon may react. So 1, 2, 3 membered ring you will get. If this reacts, you will get 5 membered. So this is not possible again also. So this carbon with a negative charge reacts at this carbonyl. So giving 5 membered ring. So you will get a 5 membered ring. So let us write this C double bond. So this is 1, this is 2. So 3, 4, 5. So 2 hydrogens will be lost at this carbon. Oxygen is lost at this carbon. So what is he? 1, 2, C double bond, and 3. So this is 1, this is 2, this is 3. This is clear. 3, 4, 5. This carbon has CH3. Then this first carbon has CH2, this one. So this carbon has CH2, C triple bond, C, C2H5. Now this is treated with Lindlar's catalyst. So it is Lindlar's catalyst. So that carbon-carbon double bond will convert, triple bond is converted into double bond to give cis compound. So hydrogen addition takes place from the catalytic surface, so that it will give a cis alkene. That is what is this jasmine. So what is, we are getting T finally. So when this is treated, we are getting T. Okay. So let us see what were the questions under that. So it's a, let us say, like a comprehension type. So what is compound Q? So this is what we have a scheme of reactions here. So what is Q here? Already known, A. So anyhow, we are not getting O, that you see NO2 or ONO. So this is NO2. Now, next one. The structure of that already we had. So a double bond. So it is anyhow just cis. So this can't be the answer because this is trans. So this is cis. This is only cis. This is anyhow triple bond. So this cannot be the option. Okay. So among that A or D. But in this we don't have a double bond there in the ring because it has to form alpha beta unsaturated ketone or aldehydes. So aldol condensation. So this has alpha beta unsaturated. Our jasmine. Okay. Jasmine structure. Now, coming to next. So this was the scheme that we have to go through. So all the depending on all alkene reactions, alcohol reactions, everything mixed up in that. Now this one, it's a big scheme of reactions are mentioned here. And now what you see? The hydrocarbon, sorry, P, C11, H8 on treatment with. So when you have this scheme like continuation, your last compound will be finally an indication to move in the backward direction. So you have to move always from the product side. So there is some place or some reaction where it is a hint was given, this has to be the products. Just let us see that, where you can just identify the things first. A hydrocarbon on reaction with dilute H2SO4 in presence of HgSO4. So when you see H2SO4 and HgSO4, immediate idea is it has a triple bond somewhere. Because mercuric sulfate, we are generally adding during acidified catalytic addition of water during the alkynes. For the alkenes, directly we add normal acidified water. But even the acidified water during the alkynes will form a vinyl type of intermediate. That vinyl type of intermediate is unstable. To stabilize that, we use the catalyst HgSO4, Hg2 plus salt. So this is somewhere a triple bond was there. So it is giving Q. Means you may get ketones, or that is the only reaction that is what you say, acetylene only can form aldehyde. Remaining all terminal, non-terminal alkynes will form ketones only during the acidified catalyte. Next, P, that is the same again, treated with B2H6. Generally, we don't use that B2H6 maybe during the hydroboration reaction. We just use actually the secondary SiA2BH because the reaction becomes complicated. But you can say B2H6 also not an issue. So even the hydroboration oxidation, you can use B2H6. But the better synthesis is done through SiA2BH. So when this is B2H6 and H2O2 NaOH, it's a hydroboration, so which has to follow anti-Markovnikov addition. Then it will give a ketone depending on the terminal alkynes and non-terminal alkynes, internal alkynes. So internal alkynes anyhow will give ketones, but terminal will give aldehydes. Okay. So it's an isomer of R. So anyhow, it's only water addition, it is also water addition. So you are getting R, RQ, they are isomers to one another. But Q will give yellow precipitate, means it is giving iodoform reaction. NaOI. R does not give, means it cannot respond to iodoform test. But R forms a grey precipitate with ammonical silver nitrate, means it is aldehyde. It's an aldehyde. It's an indication of aldehyde. So R is forming a grey precipitate with ammonical silver nitrate solution. Done. So it has an aldehyde group which can't respond to iodoform test, but it will respond to tolerance reagent. Okay. So this is a tolerance reagent. On boiling with alkaline solution, that P is with KMnO4, it is giving C8H6O4. So when you just see the molecule formula, it looks like this is nothing but an acid groups are there. So alkaline KMNO4 is giving the acids. O4 means you are getting two COOH groups. So that indication like P4O6, sorry, P4O10 reaction, it is forming an anhydride. So this is an anhydride of this. See, loss of H2O will be there here. H6, H4, O4, O3. So S is an anhydride. So it is a double diacid, dicarboxylic acid, which is losing the water. So which type of dicarboxylic acids can lose water? Which are closer to that? Then they can lose it. Then S on reaction with toluene in presence of anhydrous AlCl3. It is a hint again. So benzene, things are there here in the product, final product, what you see. So it may be a anhydride with a benzene related. So which type of dicarboxylic acid will be forming? So this is C8. This is C8, H6O4 can be. Benzene is there. Then the COOH groups are suppose in ortho position. Then they can. So this formula is now C8, H6O4. So this is your compound, this P on hydrolysis. So you should have a carbon chain continuation like something in the system where it is breaking and 11 carbons are there in the original P, but it is continuing to give a reaction with KMNO4, it is giving only C8 compound. So that other carbons are leaving. Carbon-carbon triple bond. Already we started from the triple bond should exist in the comp. So toluene in presence of anhydrous AlCl3, nothing but again Friedel-Crafts alkyl acylation because anhydride is there. So T is you are getting something. Then as the major product T reduced with zinc amalgam, then the product obtained is on following reaction with PPA, polyphosphoric acid, stronger acid, concentrated acids. So some hint was there in the process and it is identified as your compound is phthalic acid. That is one of that compound you are getting. Okay. And this is an anhydride. So what was this thing you see? So if you just see in this one, what is mentioned? So you had a P which is having C11H8 formula. It is on reaction with dilute H2SO4 in HgSO4 or Hg2 plus is giving Q. It can give iodoform test. Then this compound is treated with HBO reaction is giving R. These two are isomers as I said, but this cannot give iodoform. But this compound can give Tollens reaction, Tollens reagent. So it will give a positive test. Okay. Then this is suppose treated with alkaline KMNO4 and heated. Then it is giving directly, I can write now COOH and COOH. This is when treated with P4O10 now, was giving anhydride. Double bond O, double bond O. Then this is treated with toluene. In presence of anhydrous AlCl3. So the alkylation acylation reaction has to take place because anhydride is there, plus some containing is there. So in para position to the methyl, there is C double bond O substitution. Means it is nothing but C double bond O here. So let us say this bond is breaking, this C double bond O is attacking them. Then you have a benzene ring again. So we have a benzene ring again here like this. So this is C double bond O is linking that. Then next immediate carbon. So you can just go in any direction. So next immediate carbon should have C double bond O, OH actually. So it is nothing but let us say COOH. So this is what actually he said as some compound there. Maybe some numbers are used, PQ something are used. So let us see just one page only, no? That was T. So S is that. R. So what is? So this is Q, R, this is S, this is anhydride, then we got this T. Now this is treated with zinc amalgam. So Zn, Hg, concentrated H2SO, HCl. So Clemmensen reduction. So this C double bond O part will convert into CH2. So you see methyl, CH3, CH2, COOH. Then reaction of this with PPA or some concentrated acid and heated. Then what happens? This acid group, OH group is lost and this C double bond O again attacks in the ring. But where it can attack? This ortho position to this. Because this is plus M group, this is plus M group, but para position was blocked. So its ortho position or this ortho positions can react. But this ortho position is not possible. So the adjacent C double bond O can react. This C double bond O can react at this. So what you see is CH3, this C double bond O, then there is a benzene ring. Clear? So this carbon is C double bond O is attached to benzene rings. So both these carbons are attached to benzene rings. So just write carefully. C double bond O. This is attached to benzene ring. This is attached to benzene. So you can write these two carbons and adjacent carbons. So this is your benzene ring. Okay. There is a carbon in middle. So you can just write little bit curved. This one curved. Okay. So here also a 6-membered ring is there. 1, 2, 3, 4, 5, 6. So that is what he represented here clearly. So this one. CH3, its para position is CH2. So there is a benzene ring, C double bond. So that original molecule what we had, 6-membered ring in the middle. So what is our P? Maybe it should give Q with the acidified water addition, haloform reaction, but with hydroboration it will give a compound which will not give haloform reaction, but will give tolerance test. So what can be your P? What can be our structure of P? So it should be having a carbon chain here with a triple bonds. What is this indicates? So P can be like this, no? Suppose you have a carbon chain with this C, a triple bond is there, let us say with C. Then there is a terminal thing. Then you can write another terminal thing. So that both ends will get aldehydes if hydroboration is done. Then it can give a positive test, tolerance test, and it won't give iodoform test. But if it is written here, it may give iodoform compound also. Means you will get, because it is symmetrical, then not symmetrical, internal alkyne. Internal alkyne can give keto group at here or here. Clear? Acidified water generally gives only ketone. So ketone can be obtained here or ketone can be obtained at this stage, if it is a possible case. Mostly it appears here, then it won't give also maybe. But better you write in the terminal position. But even this carbon, if you are having hydrogen, if you are reacting with a alkaline KMnO4, so this carbon having a double bond or triple bonds, or alpha carbon hydrogens having hydrogens, then they are treated with acidified KMnO4 or alkaline KMnO4 on heating, like a stronger oxidizing agent. They convert into COOH groups. Alpha carbon with respect to benzene, benzylic carbon otherwise, having hydrogens or double bond or triple bond. When they are treated with any stronger oxidizing agents, they convert into carboxylic acids. So this C converts into COOH. So if this compound is treated with a hot alkaline KMnO4, it converts into acids. So now this is treated with, suppose, HBO. What is this Q? What R and Q? So here this can be Q, C double bond O CH3. Here it is C double bond O C2H5. You can get this side also, but very less in minor product, because double bond C plus here is a little bit more stable. So what you see, this is our Q, but this can respond to iodoform test because it has C double bond O CH3. Now what is R? This one should be, so now what is that R may be? You are adding acidified water and anti-Markovnikov. So this one will become OH and H. So this will become CHO, this will become CHO. So what is this is CH2, CHO, CH2, CH2. So this is the structure of R. Okay. Now, coming to the questions what we had now. This is also, I think, a comprehension type for us. Sorry. So this is the thing. Now let us see what are the questions under this. So this is what we said. So which of the following products are formed when Q is heated with sodium hydroxide? So what was Q for us? Q was, this was Q, C double bond O CH3, C double bond O CH2 CH3. So this alpha carbon can react at this. This alpha carbon can react at this. So possible means which of the following are formed. So as you just see the options, you can see where it is. So if this carbon is reacting with this, clear? Or maybe you can see the other thing also, other possibility. No, we written the triple bond at the end, no. So sorry, 1 minute. This thing we have written wrong because it is here. Why problem is coming with. So this is our CH2, C double bond O CH3. Terminal positions we kept to avoid the So the acidified water, it always gives ketones. So now this one is Q for us. So this is a Q for us. This was a Q for us. So CH2, C double bond. So this carbon reacting here, it's again saying this carbon reacting here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you will get a 6-membered ring, either of the way. So this O, this H2 can be lost. Then you may see that product. H2. So C double bond O, CH, C double bond O, CH3. This you can get fourth. If this reaction, if this is reacting here, then you will get this 1. So if the reaction is between these two, you will get 1. The reaction is between these two, you are getting the 4. So 1 and 4 we will get. Okay. So if Q reacts are treated, aldol condensation is done. Coming to the next. S on heating with. So what is S was? S was an acid and phthalic acid. S was phthalic acid only. COOH and COOH. When it is treated with hydrazine, H2, NH2. So nothing but it is OH and OH with amides formation. So it results in this directly. C double bond O, NH, NH, C double bond O. So OH, OH, H will be. So reaction of amines with acids, ammonia with acids, it forms amides on heating. Okay. So this is directly now. Done. What is the structure of R? We said. So what is R? Which should give only tolerance test, but not the haloform test. So if this is the thing, haloform test is possible. This is the thing, haloform test is possible. This is the thing, no, haloform is not possible maybe, but anyhow, it's a terminal. This has to be the answer. Okay. So aldehydes you are getting by HBO reaction. Coming to this, let us see this. The last one, I think. So correct statement regarding the products of the reaction. So again, it's like first question for us, UV something, there we have seen this one. So what is this? Is epoxide, this is a aldehyde is there. So what may be the possible reactions that we can see? This CH3 MEO minus, it's a nucleophile. So it's an epoxide, it can open the rings. So just see here itself, I think. This O minus can open the epoxide with the less hindered side. So what you will see in the first reaction is Me3C, this Cl, this carbon with now O minus, then this is nothing but CH2 and we have OMe. But here we have a halogen and we have in the beta position negative charge. Means beta position means this is alpha, this is beta type position, not beta carbon. So when any halogen or any bad leaving group or good leaving groups, when there is a beta position with negative charge, all will behave like a good leaving groups. So this oxygen with negative charge immediately forms double bond and the Cl is lost. So what is you are seeing is the resulting this. So A is the product in the first case. Okay. Now what may happen in this? This is C minus. Aldehyde is there, this is there. So this negative charge is coming and reacting at the carbonyl carbon. This will react, this will go with oxygen with negative charge. So you will see Me3C, Cl, this carbon with O minus, this is hydrogen and we have OMe. But already you just see the Cl and oxygen. There is an internal nucleophile is there and a halogen is a good leaving group halogen. This oxygen can give so that Cl leaves. So you convert into epoxide. So you are getting again that epoxide type. So you will see Me3C, this is O, at this carbon we have again OMe. We are reacting again, suppose second equivalent again. What will happen? This will open again because this is bulky. So OMe comes here again. So OMe approaches here again. Then you will see the formation of B. Because anyhow, alcohol is there, that O minus gets protonated and converts into OH. So B is the product of this. So A is the principal product in the reaction 1. B is the principal product in the reaction 2. So for us, first statement is correct. Okay. Next, B is the principal product in reaction 1, A is the principal product in reaction 2. No. In both the reaction, a mixture of A and B are formed in the reaction 1:2 ratio. No, because this is directly undergoing the elimination there. No. B is the only product formed in the reaction 1 as well as in the reaction 2. No. Because reaction 1 directly gave the C double bond O part. Even suppose you react excess, then it reacts here, then it is not giving resulting this. Anyhow, you will get OH, you will get Me, you will get here, not at this carbon. So it's like acetal type formations here. Okay. Because this was an aldehyde carbon, this was converted into OMe and OMe. Acetal formation has to take. Huh? So this is the thing. So just we see, let us see any slide is there for us, any other question is there. We just continue for one more 5 minutes. Okay, now, okay. Is there. How many of the following will give silver mirror test? So silver mirror test can be given by all aromatic and aliphatic aldehydes, alpha hydroxy ketones, formic acid can give. Formic acid immediately get oxidized to CO2. Formic esters can give. Then alkyl hydroxylamines give. That is NHOH will give. Clear? It can be given by terminal alkynes. It can be given by polyhydroxy compounds. Like we have catechol, ris-arsenal, they can give. Clear? So there is a list of compounds which are able to give the silver mirror test. So the aldehydes are converting into acids. Alpha hydroxy ketones are converting into diketones. The OH group is oxidized. So what are these here? This is what we had. This is aliphatic, formaldehyde, formic acid, formic ester, alpha hydroxy ketone, hydroxylamine, methyl, aromatic aldehyde, C double bond O, CHO. CHO is there. C double PH, C double bond O. Glyoxal can give, sorry, in the list, glyoxal can give. Glyoxalic acids can give. Para-hydroxy benzaldehyde will give. Acrolein, that is CH2 double bond CHO, vinyl aldehyde. So all can give. So list how many? 5 there, 5 here, 2 here. Clear? All are giving you the list of compounds which are. Okay? So now, so we'll end with this session now, and hope it's clear, and we will see the next session maybe if possible. Thank you. Okay.